We talk about oil like it's just one thing, but it's not even close. Oil has this secret biography, this hidden story that starts with ancient life and ends up as the liquid gold that, well, powers just about everything. So let's dive in and uncover how oil gets its many different identities. Okay, so just look at these two. On the left, you've got light sweet crude. It's a liquid. It flows like water, pretty much. But then on the right, that's bitumen from oil sands. It's so thick it's basically a solid. And yet, believe it or not, we call them both oil.
And that's the big puzzle, isn't it? They look and act completely different. So how on earth can they both trace their roots back to the very same starting point? Well, to answer that, we've got to go way back in time.
Turns out, every single drop of oil, no matter what it looks like today, starts with the exact same recipe. And it's a recipe that takes millions of years to cook.
It all starts in ancient oceans with tiny little life forms. Think plankton, algae, that kind of stuff. When they die, they sink down to the seabed. Now, here's the crucial part. They get buried by mud and sand so fast that there's no oxygen around. That means they don't just rot away. Instead, as they get buried deeper and deeper over millions of years, heat and pressure start to work their magic.
But here's the thing. This preserved organic gunk isn't oil. Not yet. It's this in-between stage called kerogen. Honestly, the best way to think about it is like raw dough. It's the starting ingredient, just sitting there in the Earth's crust, waiting to get cooked into actual crude oil.
And how long does that cooking process take? We're not talking hours or days. To turn that kerogen dough into crude oil takes anywhere from 10 to, get this, 100 million years. I mean, that's a timescale that's just hard to even wrap your head around.
Okay, but this is where the story gets really good. Once that oil is finally formed, its journey is far from over. This is where it hits a massive fork in the road, the moment that decides its final destiny.
Right, so that initial creation is just step one. As soon as it's formed, oil starts to move. It migrates upwards through porous rock. And its ultimate fate, whether it ends up as that light, easy-flowing liquid or that heavy, thick sludge, depends entirely on the path it takes from here.
And there are a few key things that shape that path. First up, depth and temperature. Does it stay buried deep inside the Earth's hot kitchen? Or does it wander off somewhere cooler? And then there's this thing called biodegradation, which is basically a fancy way of saying, does it get attacked by an army of hungry microbes?
This biodegradation process is wild. Imagine the crude oil is a giant buffet. These tiny bacteria show up and start feasting, but they're picky eaters. They go for the light, easy-to-digest hydrocarbons first, kind of like how we go for the appetizers and dessert and leave the heavy stuff for later. The more they eat, the thicker and heavier the leftover oil becomes.
So when you put all those factors together, you end up with three totally different fates for our new oil. It can be protected, keeping all its good qualities. It can be degraded, losing some of its value. Or it can be completely transformed into something else entirely. Let's look at each one. First, we've got the best-case scenario, light sweet crude. Now, light just refers to its low density, which is measured on something called the API gravity scale. Sweet is simple. It just means it's low in sulfur. And most importantly, it flows easily, which makes it super simple to pump and refine.
So how does it get to be so perfect? Basically, it gets lucky. This is oil that stayed buried deep, where it's so hot that those hungry bacteria can't survive. It was also protected by a good seal in the rock, keeping it safe from groundwater. It's like it was kept in a perfectly preserved time capsule.
All right, now for destiny number 2, heavy oil. This stuff is pretty much the opposite. It's got a high density, which means a low API gravity. It's thick, it's viscous, and it's got more sulfur. All of that makes it way harder and more expensive to turn into things like gasoline.
And get this stuff usually started its life as high-quality light oil, but somewhere along the way it took a wrong turn. It migrated up into shallower, cooler parts of the crust where those bacteria could survive. And over millions of years, the microbes just went to town on it, degrading it into the heavy stuff we find today.
And that brings us to our final destination, the most extreme transformation of all, oil sands, which are packed with bitumen. Yeah, this is that nearly solid stuff from our first slide. It is so incredibly thick and heavy that you can't pump it like normal oil. It's closer to the asphalt on our roads than the liquid fuel we put in our car.
This is what happens at the final stage of degradation. This oil migrated all the way up near the surface, where for millions of years, bacteria had an endless all-you-can-eat buffet. They ate pretty much all the lighter parts, leaving behind only the heaviest, most complex gunk,
which is now all mixed up with sand.
Okay, so we've got these three totally different life stories, all driven by geology. But why does any of this ancient history matter to us, right here, right now? Well, it turns out that geological journey has a very direct impact on our wallets.
So this whole complex story, the heat, the depth, the migration, the microbes, what's the bottom line for us? It all boils down to one very practical reality.
And here's where it all connects. You can see this perfect chain reaction. The journey, deep versus shallow, protected versus eaten by microbes, it directly changes the oil's physical properties. And those properties, they dictate the most important thing, how we get it out of the ground. Light oil is easy, you just pump it. But by the time you get to oil sands, you're talking about massive, energy-intensive mining operations.
It really is that straightforward. An oil's multi-million-year-old biography, how it was cooked, where it traveled, and what tried to eat it along the way, that directly determines its price tag in the modern world.
I mean, this just says it all perfectly, doesn't it? It's a powerful reminder that deep beneath our feet, geology is constantly writing and rewriting the story of one of our most important resources.
And that leads us to a final, really critical question. The story of oil's past has clearly shaped our present. But as the easy oil, that high-quality, protected, light, sweet crude, gets harder and harder to find, what happens next? It's definitely something to think about.